So welcome everyone. So we shall be starting lecture 4, and this is going to cover motion of particles, where we shall look at relative motion of particles, among others. But to take you just a step behind, you must have understood the previous chapters for you in order to understand this chapter. And also your knowledge of calculus should be updated. Otherwise, we are going to be moving steps that need you to, first of all, go review your simple calculus, right? As well as I am going to send support videos, because what I'm going to teach here is just quite on the surface. So that means that you need to stretch more and understand. So I'm going to put some YouTube videos that you're supposed to watch. I'm going to arrange this as video 1, video 2 until the last video, so that you have support information or support lectures that are going to help you understand this more. I'm also going to share the books. Please make sure that you discuss these things within your discussion groups, right? To understand this very well. Right. So now we are going to look at motion of particles, right? We're going to look at motion of particles, and precisely, first of all, we are going to look at relative motion. Now, let's take this example. For instance, for particles along the same line, time should be recorded from the same starting instant, and then displacement should be measured from the same origin in the same direction. So if we are to tackle relative motion or particles or that are in relative motion, we need to take this into consideration, that time should be recorded from the same starting point of the instant, as well as displacement should be measured from the same origin in the same direction. So we are going to see this, and also in particles moving in straight line, as well as we're going to look at this in pulleys, okay? But first we are looking at this in particles that are moving in like linear motion or in straight line. So now we are going to consider particles. We are going to say at this point, which is our origin, starting point O, and this particle moves to point A here, as well as moves to point B, right? So that means that we have distances from, the distance from O to A, B, a distance XA, and also the distance that is measured from point O to point B be called XB, implying that the distance of B relative to A is given by XB/A, meaning this is called the distance of B relative to A. So which is given in this case, the distance, which is, or the displacement, which is of point B relative to point A, which is X subscript B over A, is given by the difference between XB and XA. So that's what we call the relative position of B with respect to A. So that means from this equation right here, we can now deduce what XB is, meaning that our XB is given by XA plus the relative displacement or relative position of point B with respect to A. Now, you realize that from the same equation right here, right, we can also differentiate, right? If we differentiate this, so we differentiate XB with respect to time, we are going to have velocity. That means that the relative velocity of point B with respect to A is the same as the relative velocity of so the same as the velocity of B minus the velocity of the particle at point A. So that means that V subscript B over A is what we call the relative velocity of particle B with respect to A. Again, if we differentiate that with respect to time, we are going to get acceleration, right? If we differentiate that, we are going to get acceleration, meaning that if we differentiate this thing a second time with respect to time, we are going to have relative acceleration of point B relative to A is the same as the acceleration at point A minus the acceleration at point B. So that means that acceleration at point B is the same as acceleration at point A plus the relative acceleration of point B with respect to A, right? I hope that is very clear to all of us, okay? I hope that is well understood. So now, let's look at an example. Okay, let's look at an example. Remember, there's a video that we are supposed to watch, which will be talking about this relative velocity acceleration in the linear motion. Skipping a lot of things, but I believe that once you first watch that video, then this what I'm teaching will make sense to you. So let's take an example. So a ball is thrown vertically and from a 12 millimeter level in the elevator shaft with initial velocity, which is 18 meters per second. So now, when you realize at this point, when you come to this point right here, at this point, the distance here from to this point is given by 12 meters, right? And the ball is thrown vertically, right? With a velocity of 18 meters per second. At the same instant, an open platform elevator, it passes, right? So there's an open platform that passes this ball, passes at passes a 5 meter level. So it passes at a 5 meter level, moving upward. So the ball is coming downwards, whereas the elevator open platform is moving upwards at 2 meters per second. Right? So these are two particles. We have a ball, and we have an open platform elevator, which is also moving upwards. The ball is moving downwards, as the elevator is going upwards, right? So now they want us to determine, first of all, when and where the ball hits the elevator. Okay. Again, they also want us to also determine the relative velocity of the ball and the elevator at contact, right? At what point? First of all, does the ball hit the elevator? And secondly, the relative velocity of the ball and the elevator at contact, right? So now that's what we need. So what we need to know is, first of all, we said we need to draw a diagram and then try to illustrate these things. So I hope you're going to follow this example step by step, right? So we're going to do step by step and then we're able to understand, okay? So now let's start. First of all, let's start with the ball. So initially, the ball when it was being thrown, our time is equal to 0, right? When the ball was thrown, at that ball, the time is equal to 0. But remember, the ball is thrown, and also there's an elevator going up. So this elevator will find the ball at some point, and that point, we are going to call that point at time t. Okay, let's call this t, at time t is equal to t. That's when the ball and the elevator will be in contact, right? So we need to find that, right? So, but remember, the ball was thrown at this point, which was at t is equal to 0, but that distance there was given by 12 meters, okay? That is the y naught. But also we need to find the distance, right? Now, this distance where the elevator will meet the ball will be given by yb. So which is this distance, right? Which we also want, okay? So now we are going to remember now, since this is being thrown vertically, that means that our acceleration, if it's going down, acceleration will be 9.81 meters per second, right? But now because they're going to be this elevator moving up, the acceleration is against gravity. That's why it is negative. So our A is minus 9.81 meters per second. So now remember from our second lecture, I think we were able to derive these equations whereby we said V, that was our second equation, which we say that velocity at a given point will be given by V naught plus AT plus AT, right? Remember, we derived this equation. We say that V is the same as the final velocity is the same as the initial velocity, v naught, right? Plus at, right? Plus acceleration times time. So now, let's say at that point, which is point B, we need to find its acceleration, right? So let's say this is our point B where the ball and the elevator are going to meet. That's our point B, right? So now if that's our point B right there, so that means that if that's our point, so we need to find the final velocity at that point. So now at final velocity, remember the ball is moving at V naught, which is our initial velocity, which was given as 18 meters per second. So now our initial velocity, we are going to put in our initial velocity here as 18 meters per second. Our acceleration, it is negative, which is 9.81 meters per second. And then we don't know what time it took for them to be at point T. So we need that time, we shall just call it T. So we just substitute in that equation, and then we are able to have this equation right here. Again, well, let's also remember we developed or we got an equation that incorporates the distance as well as the speed as well as the acceleration. That was the third equation we developed in the lecture 2. I think that was lecture 2, whereby we got our S as being equal to S naught. Remember, we said S naught plus a VOT, the initial velocity times time, right? And then plus a half AT squared. Remember that equation? Plus a half AT squared, right? Remember that equation? Yeah, that's the equation we derived it. So now the same thing, that's what we want, because we have this distance, we don't know it, but we want to know at what distance these two get into contact. But remember, we have our initial distance, which was y naught, or which was 12 meters, remember? So at 12, our S, now we want to find the YB, which represents the S. So our YB in this case would be given by, right? Would be given by our S naught, which will be 12, which is at here, plus our initial velocity was 18 meters per second, times the time which took, which we don't know, the same time here, which we substituted. Okay, so we have 18. These are meters per second. Please don't be confused. Times the time, which is the V naught right here. Okay, this one here. And then plus a half. Remember, acceleration is negative. That's why we have a minus right here. And then a half AT, half of 9.8 is 4.905, then T squared. So that's why we have this equation. Now remember, that one is only for the ball. Okay, so these equations are just for the ball. How about for the elevator? Okay, so this is for the ball, and then we need also to get for the elevator, right? Okay, so now we are going to now consider the elevator, because that was for the ball. So now when look here for the elevator that is moving, initial position of the elevator, they told us it was more, initial velocity was 5 meters, right? Remember, in the equation, in the question, the elevator moved until it was y naught was 5 at a time which was t, which was 0. Okay, and they told us the elevator was also at that point was moving with 2 meters per second. Okay, so now we need to find this distance where they met with the ball, which distance is YE. Okay, and they met at a time which was t, right? So now remember, this is what we are going to substitute. Remember, the velocity at that point, VE, was 2 meters per second, right? That was the velocity it moved with, right? So now remember, we need to look for an equation that relates distance as well as velocity, because also we have acceleration. But we know that our y is the same as y naught plus VET, right? So remember, we also have that equation whereby our S, right, is the final is the same as S naught, okay, plus velocity, right, times the time, because velocity times time, remember that. So now at this time, our S is YE, which is right here, and our Y naught was 5 meters, which is right here, and then our velocity, which was moving with relative to the before the ball, this open elevator was moving with a velocity of 2 meters per second. So in a given time, we can find that distance, right? So we said that we have 5m plus 2t, right? These meters per second is just units. Okay, so now we are going to relate. Remember, YE is the same as the YB, and then we are able to define the time. Okay, so now from there, we are going to proceed with our equation. Now you realize that write equation to relative position of a ball with respect to the elevator and solve the relative equation. That means that YB is the same as YE. So what we are going to do is that we just equate, and when we equate those equations, we are going to have something like this, and we are going to form a quadratic equation. So when you solve this quadratic equation, you're going to have 2 points, two solutions. One will be this, and another one would be that. So that means we only take positive values. So our T would be 3.65 seconds, right? So realize that this elevator as well as the ball, they met after 3.65 seconds, right? I hope that is very clear. I hope that is very clear for everyone. So now remember, we need to substitute and then get YE, and also we can also get the relative velocity, or which is relative to, the elevator is relative to the ball, right? So now from our equations, we have got T. Remember, we got our equation whereby it was YE is the same as Y naught plus VT, right? So from that equation, we got our time as 3.65 seconds. And remember our initial velocity, sorry, our initial distance that the elevator had moved was 5. So realize that the distance YE would be 12.3 meters, okay? But also we need to get our velocity, right? Remember, we need to get our velocity, which is our velocity of the ball relative to the elevator, will be given by, now we just substitute in one of the equation as 18 minus 9, or this is T minus the 2, right? So it is the velocity by which the ball is moving minus the velocity of the elevator. So which is, now when you substitute in here, because remember our velocity is the same as V naught, okay, minus AT, okay? Remember, okay, our V is the same as V naught, right? Minus, okay, it's not minus, it's a plus AT, right? Remember that equation. But in this case, we need to get our V. Our V naught was 18. Our A is 9.81, but remember, it is moving in the opposite direction, so it becomes negative. And then our time, which we have, which is 3.65. So but remember, that's what we are doing. And then the other particle is moving with 2 meters per second. So if we want to have the relative velocity of the ball, it's just the velocity by which the ball is moving minus the velocity by which the elevator is moving. So it's what we are getting. So the velocity by which the ball is moving was, you substitute in, right? Just substitute in here. You realize that the relative velocity will be minus, meaning it is moving upwards, right? Because now the elevator was moving more than the ball. So that means that the relative velocity is 19.81 meters per second, right? So meaning it was moving upwards, right? So we are going to conclude that our relative velocity was 19.81, meaning it is moving upwards. So now, having done that, that was linear motion, where we have relative motion or relative velocity, relative when a particle is moving to relative to another particle. But this was in the straight line. But what if now we have dependent motion, right? What if the particle depends on another particle, right? What if the motion of one particle depends on the motion of another particle? But these are being held in straight line. For example, you look at a crane. When a crane is pulling or a car or a dead car, you realize that the motion of the dead car is dependent on the motion of the crane, right? So now also for police, let's look at dependent motion for police. So the position of the particle may depend on the position of one or other particles, right? For example, the position of block B right here, okay? If you have this block B right here, okay, this one here, its position, it will depend on block A, right? So since these are connected by one rope, okay, since the rope is of constant length, it follows that the sum of length of the segments must be constant. It means that if we sum all these up, it must be equal to a constant, right? So now for us to start working with such dependent motion, we need always to determine the Dow term. We are going to see the procedures by which we use to determine dependent motion. For that, for example, in this case, we're supposed to determine the datum or the starting point. So for example, your datum here is this point, right? Meaning that we can have distances. For example, let's say for this particle, we have this distance here, which is our XA, and also for this particle, we have this point, which is this point, which is XB. So for us to come up with this, realize that if we have this distance, plus this one is constant, plus another distance, which is right here, plus this distance, which is right here, okay, you realize that this becomes twice, because there's this distance, and there's a constant right here. So we realize that XA plus twice of XB, right? Because this distance is XB, but also there's this distance, but also this distance. So that means that XA plus twice of XB is equal to a constant, yeah? Right? So we are going to see that. And also there are some videos that I'm going to share that are going to help you explain more of this, okay? Because I may not explain everything. So right, that's why we have XA plus twice of XB is equal to a constant, and that represents 1 degree of freedom. Right? Right. So now I hope everyone is with me and we're moving steadily. Okay. So now let's positions of 3 blocks are dependent. Let's look at how the 3 blocks are dependent to each other. So now we have a pulley where which has block A, block B, and block C, and these are being held by the same rope. Okay, but remember we say that this rope is a constant, right? Okay, so now we are going to know that twice of XA plus twice of XB plus XC should equal to a constant, which is the second degree of freedom. So now how do we derive that? First of all, for you to come to that, you have to establish the constant. So I mean the datum, okay? You have to establish your starting point. So our starting point this time is at this point, which is the origin right here. So now realize that we have this distance, which is XA. So that means that we can also have the distance for this point, which is XB from this point, which is this distance. We shall also have the distance from here to here, which is XC, which is right here. So now from this point, we can now determine, right? And see the constants. You realize that this distance here is constant for the rope, and this one is constant, remain the same, and then this one also remain the same. So from this, we realize that twice of 2XA plus twice of XB plus XC should equal to a constant, and this is the second degree, this is 2 degrees of freedom, right? So now, once we have established this relationship, of course, some of you guys may not understand where this has come from, but I'm going to send a video that is going to explain how we come up with this. So now you realize that from these points, we have there is a derived formula whereby we have 2XA plus twice of XB plus XC should equal to a constant, right? Is equal to a constant. Note that if we now start to differentiate this, because these are position vectors, so if we try to differentiate position with respect to time, then we are going to have velocity. But now if you differentiate a constant, you're going to get 0, right? So that means that if we differentiate 2xa, we are going to have velocity of twice of velocity A, and then twice of velocity B, and twice of velocity C, meaning that this is what we have. Sorry, this is what we have right here, that if we differentiate all this, with this equation right here, we are going to need differentiate with respect to time. We are going to have twice of VA plus twice of VB plus VC is equal to 0, right? Again, if we differentiate this the second time, we are going to realize that we are going to have acceleration. Now we shall have twice of the acceleration at point A plus twice of acceleration at point B plus acceleration at point C. This should give you 0. So these are some of the equations that we are going to use, and this is some of the knowledge that we are going to use for us now to solve such problems. I urge you guys to read more ahead of this, to understand this, because me as a lecturer, I'm lecturing and I have not done much to dive into the science that you guys need to understand. But some of the videos will explain much of this because there's much to cover. Right. Okay, let's continue. Where do we apply such dependent motion? Realize that we can apply such things in this. So you can see that even when you're kicking a ball, it depends on the motion of the leg and etc. Among other things are here. So you can see these are some of the applications of dependent motion. So now, I've been talking about some of the things that we need, or the procedures for us to do dependent motion, okay? So these are the procedures that can be used to relate the dependent motion of particles moving along the straight paths or the linear paths. Only the magnitude of velocity and acceleration change, but not their line of direction. Okay, so now, first of all, whenever you're dealing with dependent motion, you need to define the position coordinates from a fixed datum lines. That means that you need to come up with a datum, okay, your starting point along the path of each particle. So different datum lines can be used for each particle, okay? Secondly, you're going to relate the position coordinates to the chord length. Look at the segments of the chord that do not change. For you look at, for example, when I was showing you in the previous here, I showed you that at this point, let me pick this. So at this point, this is constant. You realize that this is constant. You realize that this is constant, yeah, and also this is constant. So usually, because they're constant, we normally eliminate them, or we can just give them arbitrary length, and then they'll phase away. Because if we are doing the position equation, they will disappear as we differentiate. Because when you differentiate a constant, you get 0. So that's what the other third procedure is trying to explain to us, that if a system contains more than one chord, relate the position of a point on one chord to a point on another chord. Separate equations are written for each chord, right? So next, you are going to realize that one pulley may be pulling one load, and another chord of line would also pull another chord. But what we do is we write these equations of displacement separately, and then apply differentiation, and then the constants will disappear. Okay, that will be shown in some of the videos that I'm going to share with you. Okay, again, differentiate the position coordinate equations to relate velocities and acceleration. But first of all, you need to keep in this mind that keep track of the signs. Okay, so now let's look at an example. Okay, so given in the figure on the left, the chord at A is pulled down with the speed of, so this chord is pulled down at the speed of 8 feet per second. So now, first of all, they want us to find the speed of this block B. Okay, they want us to find the speed of block B. So, hint, you need to first of all establish the datum. Then after you have the datum here, then you can find you can find the position, and after the position you can differentiate. After differentiating, then you have an equation that is going to relate the velocity of A and the velocity of B. So here is the hint. There are two codes involved in this. Realize that we have here two codes, or we can say two ropes. Okay, you can say we have two ropes. There is this rope here that goes like this, like this, like that. That is the first. Okay, okay, that's the first. So I can also use another color, maybe to represent the second one. And the second one is this one here, which moves like this, like that. So there are two codes. Okay, we have the red one and we have the blue one. So now what we do is, for us to do this, establish the diagram, and then we are going to separately use one code and then also do the other code, right? So that's what we are going to do. So perhaps I can remove the drawings, and then we continue with what we're studying. So now what we are going to do, for example, define the position coordinates from the fixed datum. First of all, we are going to draw a datum, our starting point, and from that starting point, then it can give us a lead. So now from here, we see that this is our starting point right here. This is our datum, and then we can define the distance. This is SA because of the point A. So this is SA. We can also determine our distance, which is from the datum to the point B, which is our SB. But remember, because these are being put by two separate codes, then we are going to establish an intermediator, which is our SS right here. Okay, this is our SS. So from this point, then we are going to define, right? So for our point A, 4. So here, now we are going to relate, okay? So here I said for that relates position, two codes. We have police C, which is the intermediate, which relates a code, the code which we saw in red and the code that we saw in blue, right? That is an intermediate. Note that all coordinates are defined as positively downwards and along the direction of motion of each point and object, right? So that's what we are going to do. And then we are going to now start having equations that are going to relate the positions, and then we're going to differentiate with respect to time. These things are very easy, and I think it's one of the easiest. So what we are going to do is we are going now to try to define or determine the length of each loop, okay? So now we had this first, remember, let me yeah, we had this first loop, which was moving like this one here, okay? We had this rope, okay? This one, okay? So we had that rope, but remember we established our datum. Datum is right here. So this is, at this point, there's a constant, and this point there's a constant, and this point is a constant. So we may disregard that. So now look at this. We said that let L1 be the length of the first chord minus any segment of constant length. So any, this one here, and this one down, and this one down here, these ones, the constant ones, we are removing them. So we are neglecting them. So that means that we are neglecting any constant. So that means we are going to have SA, which is twice, which is this distance. So we are going to have this distance plus this distance, which is going to be twice, then plus this distance plus that distance. So it's going to be twice of SA plus twice of SC, which is going to give us our length 1. So that's why we shall have our chord, first chord, shall have twice of SA plus twice of SC, which is equal to L1. Okay, so how about if we get the second length? Okay, for us, if we get the second length, our second length will be moving from this point of the chord, and then it goes up, okay? So that means that we shall have this distance from here to here. We shall also have this distance, and then we shall have that distance, okay? But this distance is constant. We shall not take it, right? So because we're trying to avoid the constants, and then we are able to differentiate. So what we are going to do for chord length 2, which is L2, we shall have this length, right? We shall have this length, which is from here to here, which is SB right here, okay? We shall also have the length, which is from here to here. Do you see? Because we have this length, so which we've got this. So we shall also have this length, which is this one to this one. And this length here, which is this point here from here to here. And that length will be given by SB minus SC. So which is SB minus SC is equal to L2, right? So now that's what we have. So now solving the two above equations, right? We are going to solve the above equation. So that means that we are going to substitute for SC, okay? We're going to substitute for SC. So when you substitute for SC, you realize that we are going to have twice of SA plus 4SB is equal to L1 plus twice of L2 because we substituted for LC right here. Make LC the subject from this equation and then substitute, you'll be able to have this equation. Okay, so that's what we have. So now for us now to get the velocity, we are going to differentiate. If you did, because remember L1 is a constant, L2 is a constant, they will give us 0. So we are going to differentiate. When you differentiate SA, you're going to have VA. When you differentiate SB, you're going to have VB. So that's what we differentiate. So when you differentiate these other constants, you're going to get 0. So that's why we have 0 here. We have twice of VA plus 4 of VB. Because this is distance, you differentiate, you get its velocity. Differentiate this distance, you get its velocity. But remember, we have our VB as was given by, was it given? Yeah, I think it was given. It was given by H, right? So remember, now if we divide by 2, realize that VA is the same as a half, right? VA is the same as VA. So if you divide by 2, you have VA is twice VB. Also, or VB is a half of VA, right? But negative in the opposite direction if we take VB the subject, right? So we know that our VB will be, so our VB would be a negative half of VA. But remember, we have our VA. Our VA was given as 8. That means that 8 would be our VB would be given by a half of VA, but in the opposite direction. So as VA is moving downwards, then VB would be moving upwards. Therefore, the velocity of block B was given by 4 feet per second, but is moving upwards. I hope that example is very simple and very clear to everyone. All right? Okay. So now let's continue and look at this example. I think this one, you guys can try it out. I'm just going to explain it since I've showed you how to create a datum. And so this time, you're also going to do the same thing for this example, right? So remember, you have to create a free body diagram and then our sketch as we tackle this problem. So let's look at example 7. I'm just going to explain it. I know you guys will handle it. So, but remember, this is just one rope. Let's say a slider block A moves to the left with a constant velocity. So this block A moves with a constant velocity, which is 6 meters per second. Determine the velocity of block B. So what we need to do, we need to determine the datum, right? Because we have block A, we have block B, we have also we have this point C. So what we need to do, okay? So we need to find the relationship between the velocity of A, the velocity of B. But remember, we need to find the total length, okay? So we have this point, we have this point, we have this point, and then we have this point as well, okay? So now we need to find, you realize that we need to determine the datum, okay? You need to determine your datum. Where is your datum? You may decide to say, probably this is going to be my datum, okay? You may decide to put your datum here, and then you have also this distance here, okay? Right here, and also you have this distance for point, let's say for point B, and you could probably put it here, okay? Okay, so that's how you're going to do, and then you're going to find the distances for A, for B, for C, and D. But now, you guys, I'm going to leave it this as an example. I believe you're going to try it out because you never know. I may bring back these kind of things for you to calculate as because they look so simple. So now, you guys are going to try out that. I'm not going to continue to show you, draw the datum, but remember, when you get a relationship between the total length of this chord, you have your XA plus 3 of YB, the distance YB plus a constant, okay? Because you can realize there's some constant length right there, should give you the total length of the chord, right? So when you differentiate that, you realize that VA plus 3VB is equal to 0, right? But remember, our VA is 6 meters per second, and our VB is just thrice of. So when you realize this, realize that our VB would be 2 meters per second, but in the opposite direction. So if this one is moving downwards, then this one is moving upwards. So guys, make sure you understand how to get the length. This one, I'll leave it to you. How do you come up with the NB right here? So please, in your free time, during your discussions or discussion groups, make sure you understand how to come up with the total length of that chord. I'm also sending more videos for you to make things clear. Perfect. Okay, so let's continue. What I'm going to do is that I'm going to leave this assignment. This assignment, you're going to do it. This is an individual assignment, and make sure that you hand in before time, right? So please make sure that you watch the videos that I'm going to send, and also make notes on those videos for your good. For your good, remember, and I think that will be something for us. So remember, let's try to end today's lecture by saying that nothing is unexplained. Okay, nothing is unexplained. Nature is a chain reaction. Everything is dependent on something else. The smallest is as important as the largest. You realize when you look at the sun, you look at the moon is dependent on the sun. When you look at the plants, the crops, the greens that we have, they're dependent on the sun, also dependent on the soil. So everything is interdependent. Also, it's dependent onto the other. So nothing is unexplained. Thank you very much. It was a pleasure having this lecture. Please make sure that you attend to the videos that I'm going to share. They're going to help you understand this better. Please, we are also preparing for our tests. Remember, in the second week of October, please make sure that we are all aware of that. All right? Okay, and thank you. See you.